Hello, my name is Klutz Sarver, and I work with Dr. Loredana Valenzuela-Slau on accurate theoretical prediction of anharmonic infrared spectra of neutral polycyclic aromatic hydrocarbons. So my project focuses on PAHs, which are complex molecules found in the interstellar media and in circumstellar environments. These compounds have recently elevated the potential for carbon-based life outside of Earth. We concentrate on the infrared spectra of PAHs, which allows for their indirect observation, but the complexity of these molecules makes the analysis of their spectra challenging. For instance, we know that there are PAHs present, but we cannot confirm which species. And the goal of this project is to contribute to the NASA Ames PAH IR spectral database by determining the quantum mechanical and harmonic IR spectra of selected PAHs. So when the James Webb Telescope is deployed in fall 2021, new high-resolution spectroscopic evidence will be available, and more spectric data on PAHs will need to be interpreted. As mentioned earlier, the ultimate goal of this project is to contribute to the NASA database by determining the IR spectra at higher levels of theory. A few things for each species will be delivered: equilibrium geometries, determination and analysis of harmonic and anharmonic IR spectra, comparison of results with experimental data, and finally, the impact of molecular symmetry on the spectra. Two species that are examined in this poster are bicycle 2 and ethylene benzene. For the purposes of this poster, only B3 LEAP 631G with C1 imposed symmetry will be described. The quantum chemical calculations were performed with Gaussian-16. The level of theory used was density functional theory approximation, B3 LEAP, employed in combination with two atomic localized basis sets, 431G and 631G. Additionally, calculations on each PAH were performed both with no symmetry, i.e. C1, and the highest symmetry available, i.e. C2V. An important concept in infrared spectroscopy is the dipole moment. If there is no change in the dipole moment, then the vibrational mode is infrared inactive, and vice versa. Another important aspect is the potential energy surface of the harmonic oscillator and the anharmonic oscillator, as seen here in figure 2. As you can see, there is only agreement close to the minimum of the PES. The equation of the anharmonic is seen over here. With this equation, you can see the quadratic term, which is the harmonic approximation. Finally, overtones is the last concept, which are lines of weaker intensity at almost integral multiples of the fundamental vibrational modes. Then we have results. The first species I call bicycle 2. In each species, we discuss additional vibrational bands were present in the anharmonic IR spectra due to active combination of modes and overtones. I noticed that there is no difference in contributing combination and overtone vibrational modes within a basis set, so no symmetry does not affect the results. Figure 3 is the infrared spectrum of bicycle 2. With bicycle 2, the additional anharmonic band appears at approximately 3115 and arises from two contributing combination vibrational modes described in table 1, which is right over here. Table 2 shows the most intense harmonic and anharmonic infrared peaks for bicycle 2. It also shows the shift in harmonic and anharmonic as delta nu. The most intense vibrational mode for the harmonic spectra is located at 3071, and you can see the corresponding anharmonic modes in table 2. The motion of this band is seen in figure 4. The second most intense vibrational mode for the harmonic spectra is located at 3125, with the motion shown in figure 5. Moving on to ethylene benzene, figure 6 shows the infrared spectra for ethylene benzene. The results for ethylene benzene show two additional anharmonic bands. The first is located at approximately 2810 and arises from an overtone, while the second band is around 3125, arising from a combination mode, which you can see in table 3. Table 4 shows the most intense harmonic and anharmonic infrared peaks for ethylene benzene. The most intense vibrational mode for the harmonic spectra was located at 3119. The motion of this band is shown in figure 7, just up here. The second most intense vibrational mode for the harmonic spectra was at 3204. Again, this motion is described in figure 7. To conclude, the anharmonic results for ethylene benzene and M-xylene, two different species, at B431G are missing due to poor quality of such a basis set. This testifies the necessity of employing a richer basis set in order to describe the IR spectra of PAHs more accurately. Thus, the results from this project will provide better theoretical data, which will be used to compare with the data collected from the James Webb Telescope. From my project, we can see that the addition of the anharmonic approximation brings the theoretical infrared spectra closer to the experimental results because of the combination modes and overtones. There was also an increasing shift between the harmonic and anharmonic spectra as frequency increases. Moving on to future work, more neutral PAHs will be analyzed and compared with the experimental results of published literature. Currently, the infrared spectra of 12 species have been calculated and are being analyzed. And finally, we would like to thank the MSGC, which is funded through NASA, the Department of Chemistry at Michigan Tech for lab space, and MTU for access to the Superior supercomputer. I would also like to thank my advisor, Dr. Loredana Valenzano-Slau, for a wonderful 2 years. I really enjoyed working with you, and I hope you all the best.